Hello, in this video we're going to go over some of the applications of the mean value theorem. So first, for convenience, we're going to start with the definition of interior of an interval. Since we are going to be dealing with intervals that are both sometimes closed and sometimes open, but we are only talking about derivatives over open intervals, we need this definition. This is called interior of an interval. So interior of interval basically means the interval excluding its endpoints. So interior of these intervals, closed AB, closed A, open B, open A, closed B, and open AB, they are all the same, and they are all the open interval AB. And if you have infinity on one side, then it would be basically the same idea. In closed A, open infinity, open A, open infinity is open A, open infinity. Interior of the entire real line is itself an interior of negative infinity to B is the same as open negative infinity to open B, whether it is open or closed at B. So essentially it just means you are excluding the endpoints. And the reason we need that is that we define derivatives over open intervals and not at the endpoints. Okay, so first application of the mean value theorem. Let I be an interval. Suppose f and g are functions that are continuous over I. So I could have some endpoints. And we would need I to be differentiable over the interior of I. So in other words, we need the endpoints to be dropped in order to be able to talk about differentiability. Then f prime and g prime are the same if and only if f minus g is a constant. So f prime and g prime are the same only over the interior of A. We can't talk about derivatives at the endpoints. But f minus g is a constant over the entire interval. So that's something to keep in mind. Okay, so we're gonna go ahead and prove this one. So assume that f prime minus g prime, f prime equals g prime for all x. So this implies f minus g prime is in fact equal to 0. And this is for all x in the interior of I. Okay, so let's for simplicity call f minus g h, just for simplicity. What I want to show is that f minus g, which is h, is a constant. In order to show this function is a constant, I would have to show for any 2 points in the interval, the value of the 2 points are the same. So let's take 2 points inside I. Let A less than B be 2 points in I. Now, by the mean value theorem, since we know h is a continuous function over the interval, closed interval AB, and differentiable over the open interval AB, we can use the mean value theorem. By the mean value theorem, there is some c between A and B such that f prime of C is equal to f of B minus, h of B minus h of A over B minus A. So note that f minus g is continuous over the closed interval and differentiable over the open interval. Now, on the other hand, we know h prime is 0. By assumption, h prime of h prime of c is equal to 0, which means h of b equals h of a. And as soon as we know h of b is equal to h of a, h would be constant. Since this holds for all a, b inside I, h is a constant. So what we just showed is that every two values of h over the interval are the same. So therefore it must be a constant function. Okay. So the converse. We know f minus g is a constant over the interval I, and I would like to show f prime is equal to g prime. I do know that f and g are both differentiable. So since f minus g is a constant, I know derivatives of constant functions are 0. Since f minus g is constant, f minus g prime of x is 0 for all x in the interior of I. And that means f prime of x minus g prime of x is 0, which is to say f prime of x is equal to g prime of x. And that's exactly what we wanted to show. We wanted to show f prime and g prime are the same. Okay, so that's the first application of the mean value theorem. This one is called the identity criterion. So in order to show two functions differ by a constant, you need to show their derivatives are the same. This idea is the idea that we use a lot in integration. Anytime you integrate, when you say integral of x squared plus 3 dx, you found some function that whose derivative is this, x cubed over 3 plus 3x, and then you always added a plus c. You added a c. So this is justifying that the only functions that satisfy this, whose derivatives are x squared plus 3, are that particular function that we found plus c. Okay, let's get to do an example on this to illustrate the point that I just made. Suppose f is a continuous function for which f prime is equal to x squared minus 2x for all x between 0 and 1. Find f of x. So consider this other function. Consider g from 0, 1 to r given by, so we're going to go ahead and find an antiderivative of this. So g of x would be, antiderivative of x squared is x cubed over 3 and then minus x squared. Okay, so note that g is continuous and g prime of x is also x squared minus 2x, which is the same as f prime of x for all x inside 0, 1. Thus, by the identity criterion, f of x minus g of x is a constant. Therefore, f of x is g of x, which is x cubed over 3 minus x squared plus c. So this answers the question. And the question was find all of these functions, and the answer is x cubed over 3 minus x squared plus c for some constant c. Okay, so this is the basis for really all of the integral problems that you did in single variable calculus. Okay, so the next application of the mean value theorem is what we call the monotonicity criterion. So what is the monotonicity criterion? Another fact that you used in single variable calculus. It is the fact that it says if your derivative is positive, then your function would be strictly increasing. If your derivative is non-negative, then your function is increasing. And similar for decreasing and strictly decreasing. Okay, so let I be an interval and j be its interior. Suppose f from I to r is continuous and the restriction of f to j is differentiable. Then these are the conditions, these are the statements we need to prove. F is increasing if and only if f prime is greater than or equal to 0 for all x in the interior. So we need our function to be continuous over the interval and differentiable over the interior. So this is an if and only if statement. So if it is increasing, then f prime would be greater than or equal to 0. Okay, so we're assuming that it's an increasing function, and we want to show that f prime of x is in fact greater than or equal to 0 for x in the interior. So let x naught be in j. Since j is an open interval, so we would like to show that f prime of x naught is greater than or equal to 0. Since it's an open interval, I'm going to choose a sequence that converges to x naught and it is more than x naught. There is a sequence xn in j with x naught less than xn and xn approaching x naught. Now, by definition of derivative, f prime of x naught is the limit as x approaches x naught of f of x minus f of x naught over x minus x naught. Now I'm going to replace x by xn and use the definition of limit. By definition of limit, f prime of x naught is going to be the limit as n approaches infinity of f of xn minus f of x naught over xn minus x naught. Since xn is greater than x naught and f is increasing, f of xn is greater than or equal to f of x naught. So this fraction has a non-negative numerator. The denominator is positive. So the fraction f of xn minus f of x naught over xn minus x naught is greater than or equal to 0. So notice that f of xn is greater than or equal to f of x naught because f is increasing and xn is more than x naught. And xn minus x naught is positive. So the sequence f of xn minus f of x naught over xn minus x naught is greater than or equal to 0. Therefore, its limit, which is f prime of x naught, is also greater than or equal to 0 as desired. Note that this direction of the proof did not really use the mean value theorem. What we're going to do is we're going to use the mean value theorem in the other direction. Okay, so in this direction we are assuming that the derivatives are all greater than or equal to 0 and we want to show that f is in fact increasing. So take 2 points inside interval let a and b be in interval with a less than b. By assumption, f is continuous on the interval a to b and differentiable on the interval open interval a to b. So therefore I can use the monotone convergence, the mean value theorem. By the mean value theorem, there is some c inside the interval such that f prime of c is equal to f of b minus f of a over b minus a. But the assumption tells us that f prime is greater than or equal to 0. By assumption, f prime of c is greater than or equal to 0. Since b is greater than a, we have, so this guy is greater than or equal to 0. This guy is positive. So the numerator must also be non-negative, which is to say f of b is greater than or equal to f of a. And that means f is increasing. As desired. That's exactly what we needed. Okay, so this proves part A of this theorem. Part B is nearly identical. You just have to make sure you're putting the inequalities in the correct direction. C is also nearly identical, but I will go over C. Notice that part C is a conditional statement, not biconditional. So we know f prime is positive, then f is strictly increasing. So similar to A, let a less than b. Then apply the mean value theorem. F prime of c becomes f of b minus f of a over b minus a, and use the fact that f prime is positive. So it's really identical proof, except you have to drop the inequalities in the inequalities. Okay, so going back and taking a look at this theorem, functions are increasing if and only if derivative is non-negative, decreasing if and only if derivative is non-positive. But if the derivative is positive, then the function is strictly increasing. The converse is not true. For example, if you look at the function f of x equals x cubed, it is a strictly increasing function because x less than y implies x cubed is less than y cubed. But there is a point that derivative of this function is 0. F prime of 0 is 0. So it could be that the function is strictly increasing, but its derivative is 0 at some point. Similarly, if you look at g of x equals negative x cubed, it is strictly decreasing because all you need to do is to negate both sides of this inequality. And its derivative is not negative everywhere. At some point, at point 0 in this case, it is 0. Okay, so that's another application of the mean value theorem. Okay, let's look at one more application of the mean value theorem. a very important one. Before I get to that, I need to define the definition of second, third derivatives, and so on. So let I be an open interval. The nth derivative of f is defined recursively as follows. The 0th derivative is defined as just f itself. So if I write down f0, that's just f itself. First derivative is just the one that we defined using the limit definition. Nth derivative is the derivative of n minus first derivative. If a function is n times differentiable, we say it is Cn. And if it is n times differentiable for every n, then we say it is C infinity. So infinitely differentiable. Okay, so let's now look at the next theorem. This theorem is called the second derivative test. So what does the second derivative test tell us? Suppose I is a neighborhood of a real number x0 and assume that f from I to r is twice differentiable. So and assume that f prime of x0 is equal to 0. If the second derivative is positive, then x0 is a local minimizer. In the language of single variable calculus that you have learned, if your second derivative is positive, then the function is concave up. Therefore, this point would be a local minimum. Okay, so let's work on this one. And the second part is again nearly identical. If the second derivative is negative, then x0 is a local maximizer. We will prove the first part, and the second part, the proof is as I said, nearly identical. Okay, so f double prime being positive, we can just use the definition. So by definition, f double prime of x0 is the limit as x approaches x0 of f prime of x minus f prime of x0 divided by x minus x0. Now, this limit is positive. By one of the exercises that you had, since this limit is positive, there is some positive epsilon such that for every x inside x0 minus epsilon and x0 plus epsilon, this fraction f prime of x0 minus f prime of f prime of x minus f prime of x0 over x minus x0 is in fact positive. The reason the second derivative is positive, which means the limit is positive. Now, if you replace f prime of x0 by what it is, which is 0, we get f prime of x over x minus x0 is positive. Now, notice what happens if we look at x that is inside x0 minus epsilon to x0. Then x minus x0 is negative, and therefore the numerator must also be negative. But if the numerator is negative, if the f prime is negative, by monotonicity test, by the monotonicity criterion, f is strictly decreasing on the interval x0 minus epsilon to x0, and this means f of x is greater than or equal in fact it is also greater than or equal to, but it is greater than f of x0. So let's recap again. We deduce that the function must be decreasing to the left of x0. Therefore, the value of the function must be greater than the value of the function at x0. The value of the function at x must be greater than the value of the function at x0. Similarly, if x is from x0 to x0 plus epsilon, then x minus x0 is positive. Therefore, if you look at the fraction, f prime becomes positive. Because the denominator is positive, therefore the numerator must be positive. If you look at this fraction, the denominator is positive, x minus x0 is positive, therefore f prime of x must be positive as well. And this means f is strictly decreasing on the interval x0 to x0 plus epsilon, which means f of x0 is less than f of x. And that's exactly what we wanted. Therefore, f of x0 is less than f of x for all x inside the interval x0 minus epsilon, x0 plus epsilon, except for x0 itself. F of x0 is equal to f of x, but everything else it would be less than. And that's just like one final sentence, and then we're done. Thus, x0 is a local minimizer for f. And part B is, as I said, a nearly identical proof. You just have to make sure you're using the correct inequalities. Okay, so going back, if the second derivative is positive for a critical point, for a point whose derivative is 0, then it would be a local minimizer. And if the second derivative is negative, then it would be a local maximizer. Note that if the second derivative is 0, the above test is inconclusive. In other words, x0 could be a local maximizer, minimizer, or neither. Here's an example. F of x equals x cubed. 0 is neither a local minimizer nor a local maximizer. But its second derivative is 0, its first derivative is also 0. Look at x to the power of 4. 0 is a local minimizer, and its second derivative and first derivative are both 0. And finally, f of x equals negative x to the power of 4. 0 is a local maximizer. Second derivative and first derivative are both 0. Okay. So you just have to be careful. This is not a biconditional. This only tells you some information if you know the second derivative is positive or you know the second derivative is negative at a critical point. Okay, finally, I would like to apply what we learned in this example. Consider the function f from R to R given by that. Find and classify all local extreme points of f. In other words, we want to find all of the local minimum and local maximum values. Okay, so note that f is in fact C infinity. So I can freely use any of these theorems that we have really learned. I can use mean value theorem, for example. So suppose x0 is a local extreme point for f. By a theorem, f prime of x0 must be 0, which means 12x0 cubed plus 12x0 squared must be 0, and this gives us x naught equals 0 or negative 1. If you just factor 12 x naught squared, you get that. Okay, let's look at the second derivative. Second derivative of f becomes 36 x naught plus 24 x naught squared plus 24 x naught. So if you look at f double prime of negative 1, at 0 we're just going to get 0. So that's inconclusive. So we don't know actually what happens at 0. If you look at negative 1, that gives us 12. It's 36 minus 24, which is 12. So that's positive. So that means x naught equals negative 1 is a local minimizer. I'm sorry, minimizer, because the second derivative is positive, which means it is concave up. So that's a local minimizer. How about 0? So if you look at the function and subtract f of 0 from that, we get 4x, going back, we get 3x to the fourth. F of 0 is 1. We get 3x to the fourth plus 4x cubed, which is x cubed times 3x plus 4. Now, when x is positive, this whole thing is positive. If x is positive, then f of x minus f of 0 is also positive. And when x is negative, when it's close to 0, if x is between negative 4/3 to 0, then 3x plus 4 is positive because x is more than negative 4/3. So multiplying both sides by 3 and adding 4, we get this. And that means f of x minus f of 0 is in fact negative. So the first one tells you f of x is more than f of 0. The second one tells you f of x is less than f of 0. So, in other words, every interval that we take, in every interval minus epsilon to epsilon, there is some x more than 0 and some y less than 0 in this interval, such that f of x, one of them is more than f of 0 and the other one is less than f of 0. Therefore 0 is neither a local minimizer nor a local maximizer. So yes, it is a critical point, but it's neither a local minimizer nor a local maximizer. Okay, so this answers the question, part A of this question. So the only local extreme point is x equals negative 1, which is a local minimizer. Okay, and I believe I stated that here. Yeah. Okay, so now the next part is finding the range of this function. So oftentimes, in order to find range of a function in a single variable calculus, what you did was you graphed the function and then you found out what the range would be. So it's going to be a similar idea, but of course we'll have to make sure everything is completely justified. So what we are going to do is we're going to look at negative 1. We know there's a local minimum at this point. So f of -1 is, if you plug in -1 in here, we get 3 minus 4 plus 1. So in fact, it's 0. So at -1, we get a 0. Now we have to see what happens before -1 and what happens after -1. So let's just rewrite f prime of x. F prime of x was 12x squared times x plus 1. If we look back at here, we found f prime here. So it's 12x squared times x plus 1. So if we look at the values less than -1, then f prime of x is negative. So that means f is strictly increasing over the interval from -infinity to -1. And that's why f of x, or I'm sorry, I meant strictly decreasing. That's why f of x is less than or equal to f of -1, which is 0 for every x inside this interval. So here it is decreasing, so it's coming down. After that, then f prime of x is going to be positive because 12x squared is positive, or in fact greater than or equal to 0. And x plus 1 is also positive. So f prime of x is greater than or equal to 0. So that means f is increasing over the interval -1 to infinity. So f of -1 is less than or equal to f of x. Oh, I'm sorry. This would have to be also greater than or equal to, because it's decreasing. So, and that means 0 is less than or equal to f of x. Therefore, what we just showed is that, therefore, f of x is greater than or equal to 0 for every real number x. So now, intuitively, if you look at the function, when x goes to infinity, this actually does go to infinity. So it looks like the range would have to be all non-negative real numbers. So let's go ahead and prove that by the IVT. We claim that the range is 0 to infinity. So this means the range is a subset of 0 to infinity. Interval from 0 to infinity. We claim that it is in fact the same as the interval from 0 to infinity. Okay, so how do we do that? So let C be an element inside this interval, inside 0 to infinity. Okay, closed interval 0 to infinity. So we are going to find something larger than C. By the Archimedean property, there is some integer n, positive integer n, such that n is greater than C. So if you look at f of n, that's 3n to the 4 plus 4n cubed plus 1. This is greater than, I'm going to replace this one by n. This is positive, this is positive. And that's more than C. On the other hand, f of -1 is less than or equal to C, because that's 0. So that means C is between f of -1 and f of n. By the intermediate value theorem, there is some x inside the interval from -1 to n such that f of x is equal to c. So every functional value, everything in the range must be greater than or equal to 0, and everything greater than or equal to 0 is a functional value. Therefore, the range is in fact all the non-negative real numbers. The range of f is the interval from 0 to infinity. Okay, this brings me to the end of this video. So if you would like to continue with this topic, feel free to subscribe, and I will see you in the next video.